So the first thing we're going to do now is I'm just going to reset this thing here. And I'm going to load Supermon. Jim Butterfield, I believe. He was maybe Canadian, somewhere in North America, an absolute genius. One of the guys who wrote an awful lot of the books on the original PET, and he was a Commodore head and was a great man. Now deceased, sadly, but he wrote this. What this will do is this will give me an assembler, so I won't have to hand assemble this stuff. It'll be slow enough. So here's Supermon. So what does this do that we couldn't do before? It basically lets us assemble it. It's not a full symbolic assembler by any means. We can't have labels, we can't do multiple passes. It just assembles directly into memory, but you know, that's much better than having to look up all these opcodes and do them. So we're gonna go into the same place again, 033A, and we want to write a little program now which will do filling the screen badly. So this I can remember doing this all those years ago, because I didn't really have a clue, and I knew I needed to get the screen, be able to fill the screen with a character or fill a chunk of the screen. I mean, obviously they're all variations of the same sort of thing. So if we look at the code I have here roughly, what my approach was, and this obviously did not take up because I don't think we had like a monitor which could do assemble at the time. This would have all been hand assembled too. But what we decided to do, or I decided to do, was we have an instruction here, store accumulator in 83E8. So 83E8 is one past, and we'll get to why it's one past, but it's one past the bottom of screen memory. And we just keep jumping in this loop, filling the same byte over and over and over again. Not very useful, I hear you say. But this is where, and I must admit, when my initial few years of programming as a kid, I mean, I would have been, I don't know, 13, 14 when I started doing this, I suppose. An awful lot of self-modifying code was right. Now, that would shock and horror a lot of people today, but it was, you know, it looked like what you needed to do at the time. So what I'm going to basically do here, and just to show you how it's obviously not a particularly sensible thing to do, and nobody would write code this way, but it was how to a person of like me it seemed that you needed to do it at the time. So what I'm going to do is I'm going to write this program to actually modify itself. So the code here is going to change this store instruction on the fly. In effect, this program is reprogramming itself on the fly to hit different memory areas. So let's have a quick look at this. I'm just going to get some of it typed in quickly because otherwise this video is going to be an hour, and it's probably going to be an hour anyway. So load accumulator with, now what's going on here, I suppose we'll explain this. Hash dollar is obviously when we're in the system, the dollar sign means it's in hex. The hash is an immediate value. We're not saying go to the memory location E8 and look up something. We're saying no, hang on guys, E8 is the value we want. Then we want to store that, and again this looks fishy because it says FFFF, and it is, but because we're hand assembling this and we've no idea really where these are going to end up, we have to do it like this. Sorry. Then load accumulator with hash $83. Store accumulator in FFF. Load. Ignore this load X. We shouldn't be doing it. Load X should be here, should be something we discover later. But again, because of the problems with actually doing modifying code on the fly in this system where you have to shift everything down, so it pretty much means typing in everything again unless you really understand what you're doing. I am going to put this in here even though we don't need it. So it's basically load accumulator X. So basically load accumulator A, store accumulator A in memory, load accumulator A with this fixed value, store that in memory, load accumulator X, or load the X register, should I really say there. And then load accumulator X, load accumulator with 1, which is the value. So here we're going to see the value we want to start pasting into memory. 0, 1. Then we can't do a label here, so I'm just going to decrement $FFFF, store the accumulator in 883E8. BNE. Now the other interesting thing just to look here, we did the decrement here, but store changes no store changes no flags. So if this decrement had actually got to 0, this BNE instruction is still ready, so that it doesn't have to be tied directly to the instruction which did it. This will set flags, this won't, so I can check here whether the 0 flag was set. BNE. So I need the location where this decrement is. So if I look here, I can, because this is a backwards reference in my code, I can do this here as I'm doing it. I can see that it's 0348, so I can just put that straight into $0348 and then RTS. At 0350. Now, I'm going to attempt to do a save on this. I've not been having much luck with this distro, so what I might do is I might just flash this snapshot. Snapshot it, just in case anything goes wrong. So in theory, we can save all this. So I can type in S. I call it go. What a great name. No, I need to put 0 colon go, convert commas, comma 08, comma 033A. And then I believe I need to go 1 past the end here, 0351. Please save. Yes, right, so we saved that block of memory out to disk, which is a very handy thing. I think the original monitor has memory saving in it as well. So, with a bit of luck, that isn't obviously all of it. All this will do is it'll start down the bottom corner and just do the first, however many there were here in the low order byte, which I am changing. So, let's just have a look at this. Disassemble 033A. So I know I have at 50, I have an RTS. Right, so the first thing I need to do is this E8. When these need to be here is because, obviously it's because I'm rewriting the program. These need to reset the program up if it's going to be run again. So this E8 needs to go where this E8 is. So this E8 is here. And this E8 is at 034, that's 4B. So this is at 034C. So I need to assemble 033C. So I'm rewriting this line. I'm going to store the accumulator, the E8. Where am I storing it again, did I say? Wherever this E8 is going. 4B, 4C. 034C. 034C. So then the next line I need to assemble is this 83 needs to go somewhere. So I need to reassemble 0341. And again, it's stored accumulator. It's the memory location in hex there. So I've got an 83 here. The 83 is here, and it's that was B, C, D. 034D. 034D. Whoa. Disassemble 033A. Let's see if I didn't make a mess of that. So the E8 is going into 034C. 034C, there it is there. And the 83 is going into 034D. There it is there. Oh, yes. Okay. So the only other thing we need to do is this decrement here. So here we have the store. Obviously the 83 is the high bit. The E8 is the low bit. The E8 is here. So 034B. 034C. So we need to change that line. So assemble 0348. And we need to change it to decrement. Instead of FFFF, we need to decrement 034C. And we've had a quick look at that, and there we go. So if I was to exit out of here, and I was to print CHR string bracket 147, yeah, and sys 826, boom, and that's the first chunk of our screen fill done like that, which is the code we had here. So the question is, like, can we get this done, finished up quickly? The answer is hopefully yes. So again, sys4, get us to the monitor, disassemble 033A, 0352, say. Maybe I don't want it. Oh, let's clear the lines out. Brilliantly. So, what do I need to do to finish it? Well, luckily, I already put, so we're going to, we're decreasing, actually, this is interesting because as well, we can see what's happened here. We can see this line of code is not how we did, because this program has been modifying itself, reducing this low byte here to 0 and stopped when it got to 0. So hopefully when we run it again, these first 4 instructions will refix this back up to be where it is. Bit of luck. Right. So instead of RTS then, what we need to do is now we then need to decrement, instead of 4C, which is this byte here, 4D, and drop this one down. So assemble 0350, decrement $034D, 34D. Now I want to compare, but what I've luckily done is I've already set. So basically when we do a decrement on this and we've dropped below 80, so we've come right back to A0, we've done the A0, 80 should I say, not A0. Then we decrement it again, but 034D then goes, say, to 79, which we happen to have nice in this LDX here. We know we're done. So I can do compare CMX $034D, 034D, no, CPX, not CMX. Compare X to 034D and assemble there. BNE, branch are not equal. Back to where we went the first time. 0348, $0348. So again, we're jumping back to 0348, which is this loop, which is modifying in place. It's annoying having these here. I just want an RTS, and I'm not sure if they'll annoy me on the line, so let's just get rid of them. I'm sure there was somewhere getting a key repeat on a PET. Hold on. RTS. So disassemble it again, 0358. Yeah, it didn't take it, did it? A0358 RTS. Right, so again, I'm going to snapshot this here just in case. No, don't want that. Snapshot. Right. X. Get rid of this. Come up here. Sys 826. Nope, not that. And there we go. The screen filled with capital A's, a fair bit quicker than basic. So I think we should still have Jim Butterfield. Well, basically this program is one of these sort of clever programs which sort of finds a little bit of memory and moves a few pointers around, because Jim Butterfield knew what he was doing on the PET. So I can kill this program. I still have the monitor in memory. I can then do line 10. Let S equals TI 20. Now this is very quick, so let's do 100 of them for I equals 1 to 100. 30. So run the screen thing, 826. Oh, I'm going to have to get used to this. 40. Next I. 50. Let E equals TI. 60. Let, I don't think you need let actually. Let T equal open bracket end minus start close bracket divided by 60 to get seconds. Print inverted commas time semicolon T. Select 120. Well, and it's running. So 3.9 seconds to do 100 though. So, I mean, we're seeing the speed difference. I mean, for this, so that's 100 screen fills using this, and this isn't even particular, but this is how I thought you wrote machine code. Now, quickly, before everybody gets way too bored, we're just going to have a quick look at how you should do it. I'm not even sure it's worth typing this in. But basically, the 6502 has a very special mode called indexed indirect, which is tricky enough because it has the first page of memory. By page, I mean the first 256. I mean, technically, they used to call them each page had 256 bytes in it. The amount of memory that could be addressed with a single byte is 256, and then there was obviously 256 pages in the 64K of memory. But basically, what you need to do is this. Things in the first page, i.e. the first 256 memory locations, are said to be in page 0, and they are special. You can use one of them to do this indexed indirect addressing. So you can type store accumulator, and basically goes to this location which I've picked here, BB, and because of the way the PET was designed, there is not a lot of memory locations under 256 bytes free that you can use, but you can do things with them. You can pop things onto the stack, or you can try and save things, or you can, if you know certain things aren't going to be happening when your program's running, you can use them. So there is a bit, but basically you can use this to take the value that you find in there, add Y onto it, and use that to index. So this program will perform a fair bit better because it's reliant on using both the X, the Y, and the accumulator. So if anybody wants to, they are more than welcome to have a go typing that in, playing with the Vice PET emulator. It's happy days. But anyway, this was many years ago, and this is what got me into coding and machine code in the first place. And it's, as you can see, it's a long way from here to, you know, writing, you know, x64 or 32-bit PC machine code which has to interface with Windows or whatever, or even playing, you know, silly computer games like Shenzhen IO, which for those who are still watching, both of you, yeah, I kind of stopped doing it because it's only in early access and they keep changing it. So you do a level and it's not the same level anymore, and oh, they've changed this and you can do that. So it's one of my few little gripes with early access. I think I'll just wait for the game to be done and then just do a playthrough for it, rather than, you know, playing a game which is changing underneath me. And anyway, but it's a minor point. A lot of people enjoy the early access. I'm not sure I'm a great fan of it. But anyway, that's just me. So anyway, I hope those who are still watching this did enjoy this. It has been a trip down memory lane for me on the PET. There are plenty more home computers yet, and I might just pull a little bit out of one of them and just see, because like after doing this, I got into some of the more nefarious, well, it wasn't long before we had VIC-20s and Commodore 64s, and people would come along with discs and the games wouldn't let you copy them, and that seemed to be horribly unfair. And at this stage we had plenty of, for the rest of the school, we had plenty of books and knowledge about machine code, and an awful lot of my early assembler experience was then trying to reverse engineer people's codes and, you know, make a copy of a game, which we probably shouldn't have been doing, but we were kids and that's what we did. And, you know, I don't really, you know, it became far more challenging to actually, you know, try and figure out how these games were written and how they were protected. And then be able to defeat them in machine code. So, because you had to be able to, like, you know, understand the machine code and re-inject it and discover how to make the game do what you wanted to do, which was all tremendous learning in terms of code. And then we had things like ZX80, ZX81s. They were probably a little bit before this, Sinclair Spectrums, all of which got programmed. And then we, you know, BBC Micros a little bit as well. I knew people with BBC Micros, VIC-20s, Commodore 64. So I think what we could do is probably find a little bit on each one of these computers and just see what modern emulators can look at. Anyway, I hope those who are still watching this did enjoy this. As I said, if anybody wants to type this program in and see and tell me how fast it does run for 100 loops compared to my 3.91, post a comment. There will be no, there won't be a prize. I'm lying. There will be no prize, except you will be able to tell me. Well, that. So basically, if you were to get this set up here, which is the Vice emulator, just search for Vice. In fact, I have another screen here. That's where you can get it. You can get a copy of the 6502 instruction net. Some guy online has got quite a nice 6502 assembler, which is in a web page. So you can type it in and there's labels and you can sort of get your code working there and then try and get it across, or just type it in a series of numbers. Probably quicker than trying to use Supermon in many ways. So there's still plenty of people playing around with 6502. There's even some guy who's written almost a graphical, sort of fully functioning silicon version of the 6502, which is very impressive to say the least. So if anybody wants to type that program in and tell me how much faster doing it sort of properly, and even then, listen, I self-taught 6502 assembler to myself. I was never wrote a line of code professionally in it. This is many years ago, and even this is probably pretty much rubbish. There are probably 6502 guys, I'm ashamed if you're watching, but if you are, I don't know why you'd be watching, but they're probably looking at, God, that's not how you'd write that. And they are almost certainly right. I am by no means an expert on 6502 assembly, but this was many years ago and a lot of fun. So anyway, thank you for watching this. Hopefully I will kick out a few more videos in between, you know, getting on with my life, doing my boating, learning Japanese, whatever else I'd like to do. See you all soon. Hope you enjoyed it. Bye now.